Now that we have the basic structure of a hydrogen atom, it's time to expand this to multi-electron systems. We've talked about how energy levels of particle in the box and hydrogen. Now we'll see how this varies for multi-electron systems. We'll start by going into detail about the energy levels of the orbitals that we've discussed previously. We'll draw out the structures and then see how the periodic table provides us a cheat sheet for knowing the order. From here, we'll write out the electron configurations for atoms. Most of these follow pretty simple filling rules, which we will talk about. However, the D block has quite a few exceptions, and so we'll want to cover those too. We'll also talk about how to make electron configurations for ions. An electron configuration. What is it? Why do we care? Well, it states where an electron is in an atom, and it's used to explain and predict typical bonding habits with other properties of atoms that we'll talk about kind of as the quarter moves on. Using the periodic table, this is actually a pretty simple process once you get the hang of it. It does take some significant time to learn. Typically, we're interested only in the areas past the last noble gas, as this is what most affects the properties, and this will give you some shorthand for full electron configurations. Let's draw out more of the orbitals in the correct order of energy. I have drawn out two diagrams, one for hydrogen and one for hydrogen-like ions, and then one for everything else. You can see for hydrogen, all the orbitals with the same N have the same energy. So a 3s, a 3p, and a 3d are all degenerate energy levels. Degenerate means same energy. Once you get more than one electron, this causes a change in the energy levels of the orbitals. Though all three of the 2p orbitals will be the same energy, they're going to be higher in energy than the 2s orbital. You can see the next is 3s, then 3p, 4s, and 3d, all the way up through the greater energy levels. Something that's important to notice here is that even for one electron systems, these other energy levels exist. They aren't all occupied, but as you hopefully remember from our discussion on spectroscopy, electrons can be excited into higher energy levels. Similarly, for multi-electron species, just because it may only be filled to a certain level in the ground state doesn't mean that higher energy orbitals aren't possible, just that they're unoccupied unless the electrons are excited in some way. Here's an expanded version of the periodic table. This version doesn't fit well into book covers and isn't a favorite amongst publishers because of that. However, it is the most useful for filling in the energy levels and making electron configurations. So think of this whenever you look at your periodic table in the book. This way, we can make electron configurations without having to memorize the order on this slide. At first, you may find it easier to use the electron energy level diagrams that we had on the last slide, these, in order to do your electron configurations. But you really want to get to the point that you can just use this periodic table to do it. And you, of course, also won't be given this particular version of the periodic table. You'll have to use your regular periodic table. And so you need to remember that this F block slots into place there. We have a couple more rules to do a bunch of examples. Before we can write electron configurations, I think it's important to discuss how the electrons fill into the electron energy level diagrams. You'll be expected to be able to draw these and answer questions based on your drawing, and be able to do these also based on the electron configurations. So let's do carbon first. We'll start with the diagram and then build out the electron configuration from that. I drew out the diagram for the multi-electron atoms. Now, because I want to show you what not to do, I've actually started two of these. Okay, so I'm going to show you one example of what not to do, one example of what to do. These are the rules for how to fill the electrons into the orbitals. First, we will count how many electrons we have. For carbon, this will be 6. We'll start at our lowest energy level and fill up. Each orbital can hold 2 electrons, but these must have different spins. One can be spin up, one can be spin down. If there is only one orbital of a particular energy level, such as for s, you simply fill until it's full. When we get to the p orbitals, though, we have a choice. Do we fill in to one orbital, like that, Or do we go across the row? Hund's rule requires us to fill across degenerate energy levels before doubling up the electrons. So if we did what I showed in this first drawing, it would be incorrect. What we should do is draw it like this. Now, to do our electron configuration, we can write these out in order, writing first the name of the orbital and then as a superscript, how many electrons are in it. This is what we call an electron configuration. We also should talk about how to write this without needing to draw out the diagram. This is called an electron configuration and is shown here. Let's do one more like this, and then we'll discuss how to do these quickly using the periodic table. Let's do it for cobalt. First, we count up how many electrons are needed by looking at the periodic table. If we fill into the chart, this gives us 27. We fill according to the rules, which tells us to fill in from low energy to high, one spin up and one spin down in each orbital. And if we get to an orbital with more than one degenerate energy level, such as 2p's having 3 orbitals, we fill across first, and then we fill the rest. Now, I know that there's more electrons here, and you might say, why fill all the way across and all the way back, even though we're not filled up? And really, that's just to make a good habit out of always filling across first and then coming back, so that when you do come across a place where you need to do it, you'll be more likely to do it automatically and less likely to make silly mistakes. We need to make sure, as we go across the d orbitals, to fill across. In this case, it actually would make a difference if we started doubling up early. For the electron configuration, we'll write out each of the orbitals along the way with how many electrons are in them. Now, there are 2 ways to do this. We could write it out all of the way from the beginning, or just from the last noble gas. When doing it from scratch like this, where you're starting at the very beginning, it may actually, it's pretty long. We generally don't want you to do this. We generally want you to use the noble gas configuration. Now, you might be saying, well, looking at the way that we're doing this one and the way that we're filling into the electron energy level orbitals, well, when is the last noble gas? And you can tell that from the energy level diagrams, but it's a little bit more complex. Once we move to doing it using the periodic table, which is what you're going to want to do for the most part, like that's going to be how you want to solve problems, it's going to make a lot of sense in terms of starting from the last noble gas. So I wouldn't worry too much about like how do you get the noble gas configuration when using the electron energy level diagrams, because you're going to want to do it with the periodic table anyway, and it's much easier using the periodic table. It's just always good to show you where it's coming from first. Okay. So we've had some practice with electron configurations. We've practiced using the energy level diagram so that we can kind of see how these all fill. Now let's skip using the electron energy level diagram and use the periodic table. This is just way faster, okay? So, until you get good at picturing what's happening, you might want to use the electron energy level diagrams, but this is going to be how you eventually want to do it. So let's pick one to start with. I picked nitrogen. Start with here. Oops. So we want to walk along the periodic table to get to nitrogen. Helium's a little bit of an oddball. From an electron configuration standpoint, it really belongs over here. It of course goes over here because it's a noble gas, and it behaves like a noble gas because it has a duet in the first energy level rather than an octet. But for the sake of electron configurations, you need to imagine it over here. So we start here, we walk across 1s, 1s2. So the s orbitals are filled, and we keep moving until we get to nitrogen. So now we move down to here, 2s, 2, and we keep moving, and we're going to go across the periodic table. So now we're in the 2p level, and we have 1, 2, 3 electrons. So when we fill this in, we're going to get 1s2, 2s2, 2p3. We can also start from the last noble gas. It doesn't save us a lot of work here, but it'll save us a lot of work later on. So we could start from helium, write down our helium, and then move on from helium. So 2s2, 1, 2, 2p, 1, 2, 3. All right, let's do our next one. Pause and see if you can do this one on your own. And come back when you're ready. All right, let's do it. So we'll start from the beginning first and walk through it, and then we'll start from the last noble gas. So we could start from here and we can go 1s, 1, 2, 2s, 1, 2. So 1s1, 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s, 1, 2. Now that's pretty long-winded, right? So we could make it much, much, much shorter by just starting over here at neon and saying, let's start with neon. Write neons in brackets and go 3s, 2. We, again, generally, at least in my class, pretty much exclusively prefer that you use the noble gas configuration. All right, next one. Same idea here. We could start all the way from the beginning, but now we're really getting pretty crazy already, so I'm going to just start from argon. So we're going to start at argon. We would write argon down, and then we come over here. And we are at the 4s, 1, 2. Now remember, the first time you hit a d orbital is in the n equals 3 level, right? For right now, you're just trusting me on that. I'm going to explain when we get into the quantum numbers section about why we do that. Electron configurations and quantum numbers, the ordering in which you teach them is they're just paired, right? So that'll make sense later. But for now, just trust me. First time you see a d orbital, it's a 3. So this is 4s2, but this is 3d, and you have to remember that, right? It starts with 3. So 3d, 1, 2. Let's do one more. Do arsenic. Going to start with the noble gas configuration because when we're this far down, it just really makes sense to do that. So we're going to start with argon. Come over here, 4s2. We're back into the 3ds. This time it's filled, so we can count across and get 3d10. Now we're in the p section again, and that's still a 4p, right? We're in the 4s, 4p level. And you get that, 4p, 1, 2, 3. So again, try to practice this with the periodic table. If you need to use the electron energy level diagrams in the beginning, that's okay. But you really want to be able to do both. Use the electron energy level diagrams when it's useful for seeing unpaired electrons and whether something's paramagnetic or diamagnetic and how things might bond. But when you're writing electron configurations only, using the periodic table can be a much faster way to do that. Now we can do electron configurations for ions as well. To do this, we either add or subtract the appropriate number of electrons. Let's do an example of a calcium ion. Start by trying to write the electron configuration on your own, using all the material we've already covered. Here's the start of the energy level diagram if you got stuck early on. Go ahead and pause it and finish up if you need to. All right, here are the electrons. So if you got stuck before, go ahead and pause again and see if you can get the electron configuration now. And here we have our electron configuration. If you did this using the electron energy level diagram, it might be a good time to go back and see how this works on the periodic table to practice. Now, let's add in our new part. We're doing an ion, right? So this is calcium, all on its own. But I'm saying, let's also get us calcium 2+. So to make a 2+ cation, that means that we're removing 2 electrons. We typically remove the highest energy electrons, though there's plenty of exceptions to that we'll talk about in a moment. In this case, we'll remove the 2 electrons from the 4s orbital. The 2 electrons in the s orbital are removed, leaving us with the following electron configuration for Ca2+. I'm generally completely fine with leaving it as just argon on its own. Though I've heard some professors and teachers don't like this, and they feel that you should go back to the previous noble gas and work your way up. I don't think that's necessary. In my class, leaving it like this is fine. If you have someone else for these topics later on, or you're just watching this on YouTube and not actually in my class, you should really check with your instructor. Let's do an example where we make an anion, or a negative ion. Let's take chlorine and make chlorine minus. So we'll start by making chlorine. Practice this on your own. You can use the electron energy level diagram, or you can use the periodic table. Come back when you're done or when you're stuck. So here we have the electron configuration of chlorine. Now, I want us to do chlorine minus. So to give it a minus charge, that means it's got to have one more electron. So we'll need to add in one extra. This will nearly always add into the lowest possible energy level, wherever there is space for it. So in this case, that's the 3p orbital right here. So this gets added into here. This gives us 3p6 now instead of 3p5. And yes, you can write it either as this, because that's kind of what comes from just starting here and adding one more. Or if you would like to, you could switch it to argon and you could just write it as argon. Again, if you have somebody else as an instructor, you should check on that because that's not universal. That's really an instructor specific thing. Now, this is a GChem class. So we've learned a new topic in chemistry. It is now time for the exceptions because that's how this goes. There are some situations that arise that just don't follow the typical filling pattern from low to high, and then where you remove from in case of cations. So here I'm going to list them all out, and then we're going to go through each in more detail in the following slides. The first we're going to talk about involves making positive ions. When you're in the D block, you're always going to remove from the s orbitals first. Secondly, due to the fact that half-filled and fully filled energy levels are more stable, if one electron can be moved up from the s orbital to the d orbital, then it'll be promoted up. This does not occur with the p orbitals. You cannot move something up from an s to a p or from a d to a p. Okay, it's only the sd area. The f orbitals have a bunch of exceptions, but they're not systematic. We're not going to worry about them in this class. If you're interested, you can refer to the book or the internet and you can see where they all are. If I were to ask you something in the F block, just use the standard rules. I'm not going to ask you any exceptions in the F block. Okay, so why are atoms so fluid with these electrons around this SD area? So like a 4s3d or a 5s4d. The reason for that is that the energy levels are really, really close to each other. That 4s3d or 5s4d, they're really close. And because they're so close to each other and they have very similar energy levels, even though there's just a tiny, tiny benefit to having a half-filled or fully filled subshell, it's enough that it's going to counteract the fact that that electron is in a higher energy level. And so the atom is always attempting to get to the lowest possible energy level. And the added, or you can think of it as the most stable possible arrangement. And so that added stability of a half or fully filled d orbital is going to be enough to make up for that really tiny difference between s and d. So let's do examples. It's about the only way to learn this is lots and lots and lots of examples. We'll start with removing from the s block if our highest occupied orbital is a d orbital. So let's take Cobalt as our example. Probably a good idea to go ahead and pause and try to do the Cobalt on your own. I'm just going to give you the answers and such because this video is going to get really long otherwise. So here's the neutral Cobalt. Now I want us to make a Cobalt 2+. If you were following the general logic, you'd be removing from the 3d orbital, but that's not what happens. The exception here that's actually surprisingly consistent is that you remove from the s orbital first. Again, this only happens when you're in the d block, okay? If you were in the p block, you remove from the p. If you're in the s block, you remove from the s. But when you're in this d block, If you want to make a cation, you remove from the 4s. And so instead you get this. You will sometimes see a 4s0 written. Personally, I don't love that. I think if there's nothing there, it should be okay to not put anything there, and I prefer you not. However, it's not wrong. It's just drawing attention to the fact that those electrons were taken from the 4s, but it's kind of unnecessary. So I would just do this answer, right? Where you just have argon, your last noble gas, and then your 3d7. Now, the tricky part here is remembering to do this. You have to remember to do this. You can't just, like, I'm not going to have something labeled like, this is an example with an exception. Please make sure you watch the exception on the exam. I'm just going to have, here's a bunch of things that I'm going to ask you to do, and you have to know that this exists. So please be really careful about that. Whenever you do an electron configuration problem, you want to be thinking, are there exceptions? Is there things I need to worry about here? And again, I want to really point out that this is only if you're in the D block, right? If you're in the P block, you still remove from the P. If you're in the S block, you still remove from the S. So next up on our list of exceptions, we have the issue of making half and fully filled d orbitals. This occurs in these highlighted areas here that I've boxed in. More specifically, it happens when promoting one and only one electron from the nearest s orbital into a situation where you will now have a half-filled or fully filled d orbital. Practically, this means anytime you have an electron configuration, which normally you would write d4, right? So maybe you're writing 3d and you would normally write a 4, or 4d4, or in the 9. So you were going to write 3d9 or 4d9, etc. That's not actually going to happen, but that's your trigger, right? That's the thing that should remind you that there's an exception here. If you go to write it and you hit D4, you should be thinking, wait, is this one of those times I need to promote an electron up? So instead it's going to promote an electron up and be D5 or a D10 configuration. That always sounds a little convoluted when you just explain it, so we got to do examples. All right, so this is our neutral chromium. I've drawn this out. We have this ready to go. But it's not correct as written, right? Because look, we have D4. We're one away from having a half-filled subshell. So what we can do is we can promote one of these up. And now if we can promote one and only one electron from the s orbital to the d orbital, it will give some extra stability, and that will be our electron configuration. All right? So this right here is not correct. This would be marked wrong. No points. 0 points. You can't do this. Chromium is going to take this electron. It's going to move it up. Now, this only happens in these specific circumstances, okay? You can't move 2 up, right? And you might say, why? Why if I have a D3, like if I had 3D3, couldn't I promote 2 up to make it half filled? And the universe doesn't, the energy doesn't balance there. The universe doesn't do that. That's not how the energy levels work. So sometimes you just kind of have to know. And so I guess the answer to that is because we told you it doesn't. All right. Now, something else then that comes up is when we go to make an ion with these, both exceptions come into play, right? So this is neutral chromium, but there you might also be asked for chromium 1+ because chromium forms a plus ion. Same exception that we already talked about applies when you're removing. We're in the D block. It doesn't matter that we already did our exception. We're in the D block, and when we remove the electron, it's going to come from the 4s. But please notice that it wasn't that like we promoted 2 electrons up here, okay? This is a really common mistake people make in understanding this. We only promoted 1 electron up due to getting to the half-filled energy shell, okay? But then, because of the plus charge, we removed 1 from the s orbital and removed it from the whole atom. So that's a pretty common mistake that people will make. All right. So pause the video, do this, and then come back and check your answers. So write out the electron configuration for both copper, neutral copper, and copper 1+. It's going to follow along the exact same process. So if we were writing out the order of neutral copper just in terms of without any exceptions, you would get something like this. But this is wrong, right? This isn't okay because this has 3d9, which is only one away from getting a fully filled orbital. So you promote one up from the s orbital into the 3d orbital. This, even though the electron's going to a slightly higher energy, overall stabilizes the energy levels, overall makes the atom more stable, and is preferred. Now we can write out the electron configuration for it as well. That being said, you still have this one little electron hanging out in the 4s orbital, which isn't particularly ideal, and this is one of the reasons why copper so frequently forms a +1 ion, is because you can just remove that electron, get to a +1 ion, and that's a nice stable electron configuration. So we are now using both exceptions. We use the fact that we were at 3d9 to promote an electron up to 3d10. And now we're going to remove an electron, but it's not going to come from the d orbital, it's going to come from the s orbital. And we get this for our copper 1+. So if you want some practice, you can go through and do this for all the ones that do this. So the ones that do this are listed here. You should be able to know it not just from memorizing which ones do it, but like also explaining it and recognizing it, because like I can always do things like making fake periodic tables, which I have absolutely been known to do, to test that you understand this concept rather than just that you have these memorized. All right. Another very busy podcast. I try not to make them this long, but sometimes it doesn't make sense to separate them out. So hopefully that's okay for this one. We learned how to write electron configurations, how to draw energy level diagrams, and then in addition to the general rules for electron configurations, there were tons of exceptions. And so we've talked about a bunch of those and shown a bunch of examples of those. Remember, you always need to make sure that when doing these, you check for exceptions. If you don't, you're probably only going to get about half of them right. There's just that many exceptions, and they're that important. In class, we'll do lots more examples, and we'll jumble them up, right? So try to make sure you have a good handle on this, and then in class, we'll try to work on combining these concepts so that when given a list, you can say, oh, this one is normal, this one has this exception, this has this exception. Because of course on a quiz or an exam, you're not going to be told it's an exception. You're going to have to recognize them. All right, till next time.